powertrains, and electric motors. That's what we are. And Bugatti Rimac, they are for vehicles. So in
If I
our
may,
field,
if I may
more
interrupt,
technology.
I have
Yeah.
to say that I'm recording this conversation, this call, so that
Okay.
later on we will have it as a reference, and I can make it available also as a demonstration for Rimac, so that later on that you can actually, let's say, replay the presentation and I don't know, maybe look for some information again. So the call is recorded from now.
Thank you. So this is my partner, Gary Bell. Gary is our senior technical manager. And I don't know if you heard all of that, but Josip is a mechanical design engineer, and he is investigating tools for tolerance analysis, make their lives easier. You might have seen from their website, their automotive batteries and powertrains and electric motors. So we really appreciate you giving us time today. Do we have everybody in the meeting that we want?
Prahlad, I don't know if you know if someone else will join. Gary
Hey.
now King sent me a message that he'll be late 30 to 40 minutes because he has a clash, but he'll join later.
So I believe Dominic's going to join, so I will look out for him. Yeah, he's at his desk, so he should be online in a minute.
Okay. So we'll, there we go. Okay. So thanks, everybody. We'll give it just another minute or two. My name's Mike Pritchard. I think Gary might have got the spelling wrong, but you can change that real quick. It's R-I-M-A-C.
Oh. Yeah. I apologize, guys.
Sorry.
I had R-A-M-I-C, and then I changed it to R-I-M. I'm sorry.
Now it's good. Anyway.
So many thanks, guys. We really appreciate your time. What we are focused on is leveraging your CAD and leveraging your PLM to optimize your parts and assemblies and processes during your digital phases faster than ever before. The ability to make changes to elements of the design as it pertains to the build. What we try to do is simulate the manufacturing process. And we also like to take advantage of your ability to embed important manufacturing information in CATIA. So if we go to our next slide, what we're focused on is operational efficiency gains, digital operational efficiency gains. We recently had a global conference. One of our customers is Sikorsky. They use CATIA. They would get to a point in the build, process. As they were trying to stay abreast of the build schedule, much like you, I'm sure, just like automotive, aerospace. And what used to take 2 weeks, they'd get to a point it would take 2 weeks of stack ups and all that. Now it takes 1 day with 3DCS. And so they use that saved time to make decisions on other elements of the program. So that's what we want to focus on today, how you can do your stacks, but in the long run, really lay the groundwork, the foundation for a hugely efficient process that cuts the amount of time you spend between CAD and fabricating your parts. So here's the old school. Whether it's Detroit, Croatia, Shanghai, Sao Paulo, it doesn't matter, right? We design them, we physically build, we got to physically test, validate. This is the way it's been going for a long time, and it's functional, right? We do a 3D model to still flip out a 2D drawing, but when there's changes from the customer, when there's issues with tooling, when there are design requirement changes, the back and forth takes a lot of time, costs a lot of money, and impacts launch, impacts quality and production. But now you've got CATIA, you've got the 3D experience. Our fundamentals are tolerances and assembly moves, how your parts index to each other, how they index to a tool. But you can also embed that information in the experience. So you can embed GD&T in CATIA. We'll extract it with a button click. You can extract the assembly sequence in CATIA. And if it's set up right for us, we'll extract it with a button click. And this is putting our customers in a position to get to, of course, you got to do physical builds, but you get to that point with a lot more confidence and much faster than ever before. And now when the customer make changes, you'll have the ability to respond very quickly. These are our fundamentals. And I'm going to turn it over to Gary. And don't hesitate to ask Gary questions as we go through the demo today. We are going to share an electric motor with you, so should be quite appropriate. Gary?
All right, thanks for joining, everybody. So when we're going to do a 3D tolerance analysis integrated, we refer to it as a 5-step modeling process. We start out with the design. Because we're integrated in the CAD system, then you just open up your assembly and you can go to our workbench and start. We have to define how the detail components index to each other. In our workbench, we call those moves. That can be done by us, or if in the CAD system you're using CATIA's joints and constraints, then we can directly import those, and step 2 would be automatic as opposed to creating them in our workbench. We have to tolerance our detail level parts to represent the expectation of the quality of the detail components. That's the GD&T that you would put on the drawing. That can be done in our workbench or if you happen to be using CATIA's FTA, functional tolerance annotation, then we can directly import that in step 3. It becomes automatic. We have to write measurements where we want to validate our design from a dimensional standpoint. Gaps, flushes, clearances, virtual clearance to make sure bolts pass through. Those are our measurements, which again can be written in our workbench. But if you have assembly GD&T or assembly FT&A, we can pull that in as our measurements. So, because the goal is we want to know that our part tolerances and our assembly method will meet our assembly dimensional requirements. So there's really 3 main inputs: moves, tolerances, and measures. And then you're going to click a button, run an analysis, and we get to evaluate the results. So with that, I'm going to jump over to 3DX. This is 3DX 22X. Inside, it's easier for me to say V6 if you guys are okay with that. Inside V6, if you go into the compass, when our software is installed, we are right here, 3DCS. So you just click on 3DCS and you get all of our icons down here, and you can start doing your tolerance analysis. Now, one of the key things is we don't save any data on the parts. That would dirty up the parts. So if you can tell, if you're familiar with V6's manufacturing simulation or kinematic simulation, you can see up here with this arrow, that means I'm in a kinematic or manufacturing simulation. And then the model is inside that. And all of our data is saved here. There's our navigation tree, which is going to document the moves, tolerances, and measures. And this tree is linked to the CATIA tree, our tree, and the part. So if you see when I click around, it highlights it in both trees. The difference is in our tree, we have moves defined, we have tolerances defined, and we have measurements defined. You can see everything is graphic based, so if I mouse over the measurements, it's going to show you where the measurements are. If I mouse over the tolerances, it shows you where the tolerances are. And then this model is complete. So the first thing I'm going to do is I'll just assemble it and zoom in. This is a cut section through a simple electric motor. And when I hit deviate, we can speed that up, I think. Okay, you can see this thing is jiggling around. Every time this number down here changes, we're building another motor assembly. Each motor assembly is going to be different because we're independently applying the random tolerances to the piece parts and then building it, similar to what will happen on the plant floor. If I separate this, I'm going to turn my mesh on, and we focus just on this part here. You can see this part's got some GD&T on it for the position of that hole and the position of this flange. And there's some other mesh on here. If I hit deviate in the separated position, now you can see things moving around. And this is us simulating these part tolerances. So this is that flange moving, diametrically 0.5 back to the part datums. So this is us simulating piece part variation. And if I come down here and I click on the move, if I go into this move, you're just going to pick features on the housing and tell us what do they locate to on the base. So this is the move that locates this cover to the base. And there's moves. You can see this model is a subassembly. So there's a motor assembly, which consists of the motor and some bearings. And there's a cover assembly, which consists of this magnet and the housing. And there's one move in here to locate the magnets to the housing. So these moves are going to simulate the build sequence. So then I can go through here. Oops, wrong button. I can go through here and I can animate through the assembly sequence. Oh, what happened there? Separate. Whoops. Separate. Animate. It looks like the solids has got a lag, but if I animate it, the magnet goes in, the bearing packs go on, the motor goes in, and then the cover goes on. So now if I zoom in here, because the move was this cover locates to that flange, when I hit deviate from here, that flange is moving, which affects where the cover goes. Where the cover goes affects where the magnet goes. That also affects where this bearing pack goes, which affects where the motor goes. So you don't have to think about a tolerance stack path. You just have to define how your parts go together. Let me turn this back off and go into this measurement. So this is we're going to focus on these two measurements. You can have as many parts and as many measurements as you want in the model. The capability is only restricted by the computer and the capability of your CAD system. We pretty much ride on top of that. But we're going to look at that gap measurement, which is a gap between the armature and the magnet. And we're also going to look at the variation between the end of the shaft and this cutout right here. So if I hit deviate from here, you can, that's our concern. How much is that moving? And what's the gap going to do here? Oh, I think I forgot to plug my laptop in. Hold on. Just a second. Sorry, this is being recorded and I'm running out of juice. Okay, I could tell because my screen just got dim. So if I do a nominal build and we go into this measurement, you can see the nominal gap between the armature and the magnet is 0.4 millimeters. This is our goal. We don't want the gap to get less than 0. It's going to armature scrapes on the magnet. And we don't want it to be bigger than 0.7 because then the efficiency of the motor starts to decrease. So from here, if I hit deviate and I pause it, build number 41, the gap is 0.512. If I do it again, build number 69, the gap is 0.55. So once you define everywhere you want to measure and you tolerance your detail level parts and you write your moves to assemble it, that is done, by the way, with this icon to write the moves, this icon to tolerance the parts, this icon to write your measurements. As you were watching, these are all graphic animation. Separate it, build it, deviate it. Everything you do is graphic based, so if you make a mistake, you pretty much are going to see it. But then if I nominal build it, now I'm going to run an analysis. So here I'm going to build 2,000 motor assemblies. And, I only have 5 measurements in the model. That's what you're seeing here. So this is kind of a summary, first phase summary of your results. And this is, get this over here. So you can see as I click through the measurements, it jumps around on the graphics, showing you where you're measuring. This is showing you that the gap is 0.4, a mean of 0.5. The lower spec limit is 0. The upper spec limit is 0.7. And you have your estimated curve type, estimated low estimate. There's all kinds of statistics. This is just some of them that we have turned on. And if you look at it here, you can see that it's failing 8.23%, which you're seeing with this red here. And then these are the tolerances. This is essentially your stack study, 0.25, 0.5, 0.25, 0.5, 0.5, 1.15. And it's telling you which tolerance, in which part, what was the input tolerance, this geofactor, which I will get to in the next measurement, the effective Six Sigma of this tolerance, and the percent cause of variation. If you want to drill into this deeper, I'm going to double click it. And so now we can see, here's our spec limit set to 0 and 0.7. And there's the failure that we're getting, the 8.3. And at this point, I like to separate the model because I can click through these contributors and it will highlight, oops, first cause of contributor is the tolerance on the magnet. Second one is the position on the cover that the bearing pack locates to. Third one, the position on the cover that the magnets locate to. Fourth one, there's the flange back here that locates the cover. So we were talking about how all these things stack up based on their geometry. If I go to the next measurement, which was measuring the end of this shaft to the center of this hole, you will see my input tolerances are all 0.5, 0.5, 0.5, 0.5. Then you got some smaller tolerances here. But this 0.5 is 54% of my variation. Well, if this was a simple straight stack, then, if your tolerances are all the same, they're going to have the same percentage broken down. Of course, this adds up to 100%. But this is showing you that even though my input tolerance is 0.5, it has a G factor of 1.5, which means it's acting like a 0.75 millimeter tolerance on this measurement. So this, and it's easy to see, this is why we like this model as one of the demonstration models, is if I'm attaching this shaft here and here, you can see the number one contributor, come on back, is where the bearing pack locates into the base. So if the opening that the bearing pack locates shifts to the left by 0.5, this is going to shift to the left by 0.75 because it's extended outside of my locators. All of the tolerances in the list you can individually interrogate. So if I click on this and say visualize effect, and I say continue, now we're just deviating that tolerance on the base. Everything else you can see up here is held fixed. So you can get a visual of, oh, I see how this 0.5 millimeter tolerance is amplifying what's going on out here. So if we look at this results, the total range of variation is 1.01 range, or plus or minus 0.5. We're failing, 0.74%. That's what you see here. This is my number one contributor. So, if we want to say, let's quickly see what happens, we'll double click this. It will go into the tolerance. And I'm going to change it to 0.25. And then I will rerun it. We'll go back into this measurement. Got to get this, minimize this. And so now we got side-by-side variation. I went from 7.4% out of spec to 2% out of spec. That position 3, which was my number one contributor, it's now the number 2 contributor. You can see the G factor number didn't change. The only way that number is going to change is if I modify how this shaft is located. So once you get to the results of all your measurements, if they're in spec, great, you can move on. If they're really in spec, so if you look down here and you got some tolerances, you're holding this tolerance to 0.15, and it's 0.9% of my overall variation, maybe you can open up some of these tolerances that have little effect on your critical measurement. Or you can see what I just did was I tightened the tolerance that had an effect on my critical measurement. So once you get your model complete with all your moves, tolerances, and measures, and you run the analysis, at that point, if your measurements are not meeting your goals, you can change the tolerances, you can change the location method, you can change the design altogether. All of this is done before we make any parts. We're just trying to analyze our design before we start physically, spending money on real stuff. Because we're integrated, we can utilize some of the powers of the CAD system. For instance, I'm not going to do it because I'm not a V6, designer. But if I turn my mesh on again, this mesh is linked to that feature right there. So if the designer modified the diameter of that feature, our mesh would still keep its original diameter because we don't ever want to have a tolerance analysis model produce results that all of a sudden you can't replicate. But if, because we're in the CAD system, we can update with the model. So if I finish this model and 2 weeks later, I opened it up and this diameter was smaller, I can come over here and say update geometry. Then our mesh will update to the location of the new geometry. If the designer deleted this diametrical feature altogether and created a new one that was smaller, well, now we lost our connection, and this feature linking wizard here would be used to tell the software that this mesh now belongs to this new surface. Also, you can see this part has got embedded GD&T on it. So if you look over here, this is the GD&T that we pulled in. I'm going to go ahead and just delete this. So now if I hit deviate, you can see there's nothing moving here. This is moving. That's a different tolerance. That's not applied by these two GD&Ts. But because I can see this part has embedded FT&A, then I come over to this button and I say extract the GD&T. I pick the base. It says I found 5 GD&T callouts. Okay, exit. Now you can see it's here again. And when I hit deviate, now it's moving according to this GD&T. This symbol indicates that the GD&T was pulled in from the CAD. To give you an example of using our icon down here, I'm going to say I want to tolerance this part. These are all the tolerances that are already on it, which are these. I want to add another surface profile. Add. I can change the name. And I want to add that surface profile onto this surface and this surface. So now you can see those two surfaces got a mesh because now they became functional to our model. And I want to tolerance it back to A, B, and C. Okay. Okay. Now you can see down here, there's no little blue symbol. So this was the tolerance that was written in our workbench. These were tolerances that were pulled in from the CAD. And if I hit deviate, oops, cancel. If I hit deviate, now you can see those surfaces are also moving within the defined tolerance. This model does not have constraints, but if it had constraints, then you could extract them as moves. So you can see that this is the area that you extract your GD&T. If you have embedded CATIA GD&T, extract the moves. If you have joints and constraints, extract the assembly GD&T as measurements, and extract dimensioning as measures. That's what I got. Any questions?
Maybe I have one. Can you maybe apply general tolerance on the whole part?
No.
Sorry, Gary.
Yeah.
You asked the question, right?
No, it's me, Josip.
Josip, well, probably you connected from the two device.
I think I heard myself from Gary's device.
Okay, so it's not on you. Okay, sorry for interruption. Please keep continuing.
I want to ask, can you apply maybe general tolerance on part? For example, if we have a plastic component and we know, let's say that that part is TG4 tolerance on the whole part, can we just apply the dimension?
No, we can't do that for a couple reasons. Looking at this part right here, the only thing that's functional on this part right now is this front flange and this circular feature, because that's what locates the cover. This feature here, because that's what locates the bearing pack, which locates the armature. If we tried to do a general tolerance, every feature of this part would get toleranced, and then we would try to vary it, and it's going to slow the system down for a bunch of features that are non-functional. And then the other argument behind that is something that if it's toleranced to a general tolerance, then in general, that means it's not a, it's not a critical tolerance to the system. It's there to cover, hey, in case we forgot something. If, we want you to put some GD&T or define the tolerances for the features that are functional on this part. So that was my long answer. I guess the short answer is no, we can't. Sorry.
Okay, thanks.
That's a good question, though.
Just one from me. So you've obviously applied specific tolerances to specific features, and you've called out datums ABC. So do we also have to specify where the datums are,
No.
which surfaces or which features?
You don't have to. If in our software we can deviate it back to datums. That's really critical if you have subdatums. Like if you have a hole tolerance back to A, B, and C, then that's D, and then another hole tolerance to A, B,
exactly.
and D. But if you don't have any of that, you can just do something like this. If I double click here and I say position, add, I'll pick this feature here. So now I'll put a mesh on that feature. And you can see in this pull down, we have from nominal, no DRF, or a datum system. So if I just leave it to from nominal, there, this gives me a great opportunity. Our software is really smart. And it's telling me, hey, I have an M in here, which, okay, now I'm trying to put a position of 1 millimeter at MMC. But if I don't have a size tolerance defined, I can't do an M. So that's just a warning. I'm going to say, don't exit. I'm going to take that M out of there. And now it, now it will accept it. And if I hit deviate, now that hole's moving around for its position tolerance. So I always have a bad habit of wanting to show, but yeah, you don't have to have the datums. You can tolerance it, just tolerancing it. Is that good?
Sorry, I have a question. You showed before, let's say, on the example that 8% were out of let's say, the requirements. But
Yes.
where did you practically set up the requirements? Maybe I missed.
That is the requirement is set up in the measurement. So this is where, let me build it again. So the design gap is 0.4. Inside our measurement, because this is not a tolerance, this is what we're trying to validate. So the parts have tolerances, the moves build it. The measurement is where we state that gap has to vary no more than 0.7 or no less than 0, because if it's 0, it's scraping. So then when we ran the results, we'll run it real quick again. Hope I didn't change some tolerance that's going to break things up. But so if I go into this measurements, so the requirement, this 0 and 0.7 was set when I wrote the measurement. And then when we run the results, every build, we check it against this requirement, and we stack all the data on top, so you can see here's what the variation of that gap. And because we know this max is 0.7, that's how we're getting this failure of 8.14, which is just here. You can see I have no failures on the low side because this doesn't come close to crashing into the magnet.
Mm-hmm. Yeah, understood. Thank you. But let's say that here we, for example, didn't apply any CPK indexes. This would be also possible to, let's say, said that a certain a certain tolerance is also has also applied a CPK index.
Yes. First, I'm gonna go in here because this is actually a great example. I'm gonna go into my statistical output, and I'm gonna put PPK on, because now you can see based on this data and my spec limits, this has got a PP of 1. That's pretty good. That means the range of this is getting close to the range of my spec limits, but because there's a shift, my PPK is 0.47. Now in our software, we talk about PP and PPK instead of CP and CPK because we use all the data in our simulation. In the plant, you make 5,000 parts and you check 100, that's why you're using CP, CPK. But then to answer your question, got sidetracked because I wanted to turn on some more statistics. To answer your question, if I go into this tolerance, under the options, you can choose your distribution type. And then if it's a normal distribution, you can set your sigma value here. This is, this is a sigma value of 1, or I'm sorry, sigma value of 3 plus or minus 3 sigma. So it's 1 millimeter 99.97% of the time. But you can set your sigma value. It's I don't know how to explain it. It's done here, but it's not typed in as a CP/CPK. It's basically typed in as a sigma value and an offset if you affect.
Yeah. Okay, it's okay. Understood. Thank you.
I have one question more. When you added the tolerance GD&T now in this assembly, you showed that that tolerance is not linked to a part. Yes, this one. And the top ones are linked. Do you put GD&T when only using a part in some separate module, or is it also part of 3DCS?
No, it's part of 3DCS. The difference between these two, and this is a great question. If I go into this, let's say I go into this tolerance here, I can go into this tolerance, and maybe when I look at the results, I decide I can open this tolerance up. I can push that tolerance back to the embedded PMI. So if I say apply and push, it was updated successfully. And it was supposed to update. I probably need to go in here. It's 1 millimeter. You can see, so we updated it in the CAD. I got to get my graphics to update. Oh, there we go. So now it just updated. So any tolerances that we pull from the CAD, we can change the numbers as we're analyzing our results, and we can push it back to the CAD. This tolerance here that I wrote myself, that's in our workbench, and it's saved up here, in the manufacturing simulation. It's not saved in the 3D part. And if you wanted that tolerance to be saved in the 3D part, you would have to go back to your 3D experience and add it inside here. Because you can see this is the GD&T in the 3D part. And then this is the GD&T, which these two happen to be the same because we pulled it from these two. And then this one I added myself. So a typical question is, can you write this GD&T in our workbench and add it to the part? And the answer is no. We can pull from the part and push tolerances back to the part, or we can add tolerances in our workbench, which will not be added to the physical part because our tolerances, you know, they're added to the part in our tree, but they're actually all stored up here in the simulation.
Let's take 1 minute to talk about this embedded GD&T, because it's not just 3DCS that will use it. That's a machine readable file. So now it's reusable. So we have customers who will embed the GD&T in the experience. 3DCS can extract it, but it can also be used for a measurement plan, can also be used for inspection. And another point is that when Gary showed you those distributions, right, when you set up, we assume a normal distribution, but if you want to have, we've got a bunch of options for distribution, and one of those is a user-defined distribution, which could reflect measurement data. So many of our customers are using a theoretical, right? You in mechanical engineering will get declarative or speculative about GD&T. You're putting on the drawing what was either on last year's drawing or is now optimized based on some kind of study like you did with 3DCS. But the reality of the plant can change that number, and we've got the ability to bring it in very quickly and rerun analysis to reflect the plant. Think about that also for your supplier quality. A lot of customers use 3DCS to confirm their suppliers are in the spec before they ship the parts. A quick side note on advanced capabilities. Because of the nature of your products, I want to bring to your attention, I think, something that could be very interesting to you, and that's called compliant modeling. So what we do with compliant modeling is we'll grab your FEA data, we'll grab a stiffness matrix of your material, and we'll simulate how deformation, over constraint, how does thermal, if we thermally expand the parts, how does that affect our assembly variation, forces, gravity. So we have customers who use the 3DCS variation analyst. We have to assume the parts are rigid, but we've added on a bunch of extra functions that include not only compliant modeling, but mechanical modeling for kinematic assemblies. We've got gear modeling now. One of the things that Gary, when Gary was going through that process that I want to clarify for everybody is, when you establish GD&T in the experience and we extract it, we'll validate it. So you've got two levels of, let's call it GD&T security. When you're in CATIA, you've got an advisor. And then when we bring it in, we'll tell you if you missed something. Same thing when you take a drawing, right? When we do it manually, when we take a drawing and look at the GD&T and create 3D DCS GD&T, then we'll validate that the GD&T on the drawing is good GD&T or not. So don't overlook that commercial element to this process. We have customers saving $60,000, $70,000, $80,000 a part because they're cleaning up the GD&T big time. So we help our customers gain digital efficiency and further leverage their CAD system by simulating builds, the very elements of your work as mechanical engineers, now from the V6 desktop, the ability for you to make decisions rapidly. Now, after the meeting, I'm gonna send a video that one of our customers did. What they're doing is they've got a 3 DCS model. They get CATIA. They get a scan of the part. They'll take that 3D scan and tweak the geometry of the experience and then rerun the 3DCS analysis. So again, a build reflecting the reality of your inspection data and whether it's 2D or 3D. So typically how we work with a customer in Croatia, we recently won business with a customer in Lithuania, for example, and that is we can have our training is conducted in 12 2-hour online sessions. So every other day over a 3 or 4 week period or whatever cadence works for remots, we'll be able to go over the curriculum with you. And each class will have exercises and assignments. Then the following class will answer questions on the exercises and assignments and then move to the next level. Then you'll have unlimited technical support from our team. We also have partners in the Europe, across Europe, if you need regional technical support. So what do you think? Are we barking up the right tree, Josip, in your search for a tool embedded in the experience that can simulate your tolerance stack-ups?
Yes, for now it looks pretty good. Just to ask you one question about GD&T, is it both on ISO standard and ESME?
Both ISO and ESME.
Okay, great.
Okay, now I'm going to ask Gary to bring up one more slide. That's the pyramid. And this is important because this is what's going on in the automotive community right now. We showed you variation analyst. That's worst case RSS and Monte Carlo statistical output with all those distribution options. You can go very, very deep with a variation analyst model. And that is typically used by a mechanical engineer. We also DVM, design variation modeler. So our customers, instead of doing 1D linear RSS and worst case stacks in Excel, are doing it from the experience desktop. They're doing a 3D worst case in RSS stack. And so if design teams, they're responsible for design, but they want to get a quick stack of the worst case in RSS just to make sure they're heading down the right path. They can do that with DVM, very easy and to learn and use. And then if you decide as an design and engineering team that you need a deeper study of those designer subsystems, you can send the DVM stacks up to a variation analyst for a master model that can then carry it on through to statistical output and all those other advanced elements that I mentioned. Design variation modeler, half the cost as well. One last thing, viewer. This allows us to leverage Innovia. This allows us to leverage your PLM. So when Gary did his model, he can save a report in Excel, Word, PowerPoint, or HTML. And then he can save it to the PLM so that your field can pull up not only the reports, but they could pull up a 3DCS model. Very scaled down. They can't change it. they can deviate it. They can see the data associated with it. So what we've created is a dimensional platform that leverages not only your CAD, but can also leverage your PLM, can be interactive with your manufacturing teams. And help you make a ton of decisions, again, very early in the game. So how would you like to take more steps, Josip?
I'm not quite sure.
You guys want to talk as a team and then we can reconvene?
Maybe we can continue by study case. Just if you can give us an example about your user study case in the company.
Well, I need to check that out. I'm not sure if I have something right now. I don't know, maybe you guys, you have some example.
Well, maybe I can suggest. First of all, do you have any questions? Any more questions? Maybe any questions left? If not,
not for me, no.
If not, I don't know. Maybe we can. You can. I will make this session available to you on the private YouTube channel so that you can watch it. It will be only visible to you. And basically, I don't know. You can. I suggest that you. I don't know. Talk it over internally, and I don't know. I get back to you in 1 week or so and see what we can do as the next step. Is it okay with you, Rimat?
Yeah, I think that sounds fine. I mean, from my point of view, I think it all sounds pretty good. I'd be interested to sort of try it on a, as you say, like a case study on actual products that we might be working on or something that we worked on in the past, just to get a feel for how useful it could be. But I definitely can see that this has a lot of use to it, and I think I think we just need to understand how we would best implement it, basically.
Okay. Mike,
we often, very often, what we'll do is, if you've got a one of your, like you mentioned, if you've got some parts in mind, past project or just something that's Remont's parts, we are experts. We're experts in GD&T and experts in modeling. We've got 100 people focused on modeling. So we'll take your parts and we'll mock it up in the experience, and then we can have another meeting like this, but obviously it will be showing exactly how 3DCS is applied to Remont's parts. And then we could extend a copy of the software, and maybe somebody like Josip could spend a little bit of time with us to actually get his hands on the software, and we'll obviously give you a copy of the Remont's model we make. And, you can really get a good feel that for just to ensure, as you say, that 3DCS is the right tool for your longer term vision. Because what you see today is truly reflecting what we deliver to customers today. And that's why we've got so many customers across automotive. But we also understand that every customer wants to make sure that a tool is aligned with their processes. So we'd be delighted to take more steps along those lines. But a key question is, that I think you've already answered, is, we always got to know, are we barking up the right tree? Are we in the ballpark, so to speak? So if you think that and it sounds like you're confirming that, if we're 60, 70% in your ballpark, then let's use these evaluative steps to make sure we're 100%.
Yeah, I definitely think we're barking up the right tree. I mean, it's definitely something that looks useful. I just, so from a data sharing point of view, I'm not really sure how much we can really share. I mean, obviously a lot of the stuff we have is very sensitive, so we would have to sort of discuss internally before we sort of go down that route. But and I guess the other thing as well is sort of training. You know, we're talking, you said 12 2-hour sessions. I mean, that's obviously quite a long block of time that we all need to sort of free up to do that.
That's official training. I would say this is the full scale training. This is not part of the.
I definitely think though that training would be required. I don't see how any of us would be able to sort of shortcut our way into understanding how to use this sort of software to its full extent.
One thing we have been doing that might work for you is because obviously we don't want you're evaluating it. You want to make sure it looks promising. You want to make sure that it's the stuff. So what we'll do is we'll extend a copy of the software, and then we'll get into the first few. We'll have a workshop to give. Let's say it's Josip. To give them a look at the tutorial and get them headed down the path of the GUI and some of the fundamentals. And all of my customers who have taken this path have found after that first or second session that they were able to confirm that 3DCS was, aligned with their vision. Then we would proceed to making a quote for software and that formal training. And then, yes, the training would be basically, continuing on with the tutorial and then applying it to remots, parts, and assemblies once we get through curriculum.
That sounds great to me, because you cannot know before you start working on it what's the deal with it. So I like that.
Yeah, I do too. I do too, because we have a saying here in the United States, Josip, that everybody's from Missouri. And what it means is Missouri is called the show me state. So we say everybody's from Missouri because everybody wants you to show me. And in this case, it's the same thing, right? You want to be shown that 3DCS is good for remots parts and how you might use it. So talk as a team, and then if I can work directly with you or whomever, and obviously I'll keep Renato in copy, but what I would do is if I was working directly with Josip, I'd have our IT guy extend a copy of the software. And once that's installed, we could set up a workshop, same time. And over the course of a week or two, you definitely get a good feel for how 3DCS is aligned with remods.
Just one last question from me. So internally here, we have quite a specific sort of modeling process, how we generate the CAD data. Do we need to think about how we would need to modify that in order to work with this software, or is this sort of something that can be layered over the top once we produce our models and then we introduce it to this software?
Yeah, nothing needs to be, you can model your parts the way you model your parts. Nothing special needs to be done for us.
Okay, that's good.
Okay. So we'll stay in touch. Basically, now we are waiting for answer from Remats. Take a few days, or I don't know how much time do we need, and get back to us, or I can check with you and see are we ready to proceed in this direction that we somehow proposed, right?
Yeah, that sounds good.
Okay.
Hey, thanks everybody. We really appreciate the opportunity, and we work with companies that make similar products to yours, so we feel like we can bring some excellent experience and dimensional engineering knowledge to the opportunity. So I guess I'll look for a note from Josip and Renato on taking in more steps and us sending software and setting up a workshop. I'd really like to have that chance.
Okay.
Okay.
Okay, so we'll stay in touch. Thanks.
Thank you, guys.
Yeah, thanks for your time. Cheers.
Yeah, thank you.
Thank
Thanks,
Thank you very
everybody.
much.
We'll be hearing.
Have a nice
Bye.
day and talk
Have
to
a
you
nice
soon.
day. Thank
Bye-bye.
you.
Bye.
Goodbye.
Bye bye.